Recording. Hello. Okay, so I'm going to hopefully finish chapter 6 today. Just give me a sec. Sorry. Sorry about that. So I want to cover section 6.3, permutations and combinations, and then go right into 6.4, where we're going to see the binomial theorem. Okay, so this is on the menu today. And hopefully you had time to just go and look up this little example that I did in 6.1, where we counted the number of one-to-one functions from one set to another. I'm going to be using this. Okay, so 6.3, let's start with that. We're going to count subsets of a set, but in sets. Oh God, sorry. This will be edited out if I'm not too lazy. I want to count things which are ordered, and I want to count things which are unordered. And I talked about this briefly some time ago. Um, so let's start with a simple, very simple example. And I'm starting with the easier case, which are ordered things. Okay, so we'd like to count. So here's a very basic example just to illustrate the principle. I'd like to count the number of ways to select a president, vice president, and treasurer for, let's say, the student association from a set of 5 people, 5 students. Okay, so I'd like to count the total number of ways to select a president, a vice president, and a treasurer if I have 5 people to choose from. Okay, now this is not a very difficult problem if I'm just, if my job is just to count to get that number in that particular example, but that's not exactly what I want to do. I want to understand the underlying principle. Okay, so I have a set of 5 people, right? And I want to select a president, a vice president, and a treasurer, okay? So obviously, if Bob is president and Alice is vice president, it's not the same thing as Alice being president and Bob being vice president, right? So these are 2 different things. So you can see that the ordering, the way I choose the people to be president, vice president, and treasurer makes a difference when I'm counting, okay? So think of the president as being number 1, vice president being number 2, and treasurer being number 3, right? What I'm trying to do is basically count the functions that go from the set 1, 2, 3 to this set of 5 people, right? But obviously, I don't want the president, vice president to be the same person, so these functions have to be 1-to-1. So this is the number, is the same as the number of 1-to-1 functions from 1, 2, 3 to this set, okay? Hopefully you see that these are absolutely equivalent. Okay, so we saw this number to be, so we know that the number of one-to-one functions from there is 5 factorial divided by 5 minus 3 factorial, okay? Whatever number that is, I don't care, okay? So we saw a formula that tells us that, and where does the formula come from, right? It's easy in the following sense. For the president, I have 5 possibilities. Once I've chosen the president, I have 4 possibilities for the vice president. And once I've chosen this, I've got 3 choices left for the treasurer, right? So this is 5 times 4 times 3, right? Which is the same as 5, 4, 3, 2, 1 divided by 2 times 1, right? So that in this line, I've just basically done everything from the example. If you've never seen it, then of course this is too fast. But if you want to look at it a little bit, then you know what I'm talking about, okay? So this is what I want to count in general. Okay, in this example, I'm choosing 3 people from 5 and I order them in some way. I want to do this in general. Okay, so let's define what we want. Okay, so I'm going to allow R to be 0, and I'm not really going to discuss this. We can argue all afternoon about what it means to select 0 people from a set of n people. If we have time, we can talk about it, but it's anyway. So let's consider, because the formula still works when you have R equals to 0, so everything is fine. So or if you prefer, or R greater or equal to 1, if you prefer. It makes no difference. Okay, so if you don't like R equals to 0, you just start at 1 and that's fine. Okay, so I have integers R and N. R is less or equal to N. And I want to define an R permutation this is a nightmarish morning. I'm sorry, I'll have to go and kill that. Sorry. Let's pause our recording, man. Resume the recording. Okay. So what is an R permutation of a set with n elements? Okay, is an ordered arrangement of R elements of this set. Okay, or if you prefer, an R tuple with distinct entries. That's the more formal way of saying what this is. Okay, so this is what we call an R permutation of a set with n elements. Okay, so here are some very simple examples. Let's say that our set is 1, 2, 3, 4, 5. Okay, so n equals to 5. The following are 3 permutations of S. So 1, 4, 5, and 3, 2, 4 are 3 permutations of S. Right, and let's say 2, 4, and 3, 1 are 2 permutations. Okay, so you select, you take a sequence of different elements of length R. Okay, so we'd like to count how many things like this there are. So we're going to give a name to this number. Okay, so let P n R denote the number of R permutations of an n element set. Obviously, or clearly, the nature of the set makes no difference, right? If you have n elements, the number of these things will be the same. I mean, hopefully this is clear, okay? So we'd like to count what this is, okay? Now, if you go back to the example that I gave, right? I was selecting a president, vice president, and treasurer from a set from 5 elements. And I said, well, basically, I let's call president, vice president, and treasurer 1, 2, 3. I am looking at one-to-one functions from 1, 2, 3 to 1, 2, 3, 4, 5, right? So this is exactly the same thing, except it's general for N and R, right? So notice that this is the same as the number of one-to-one functions from R to 1 to R, 1 to N. Okay, if this is not like totally super obvious, clear to you, that's okay. You can spend a little time to think about this, okay? But again, if you argue as follows, so I'm going to select R elements from my N element set. Okay, so you can think of it this way, right? So we can choose from N elements for the first, right? I'm looking for a sequence of R distinct elements. So I have N to choose from at the beginning. Once I've chosen that, I'll have N minus 1 elements for the second, and I'll keep on going like this, right, until I have N minus R plus 1 for the rth, right? And by the product rule, it's the product of these things, okay? So that's another way of seeing it, but I'm just basically repeating the argument that I did for counting the number of one-to-one functions, okay? So in other words, it means then that P and R is equal to n factorial divided by n minus R factorial. That's what I want to conclude, okay? So the number of ordered sequences of length R from a n element set is n factorial divided by n minus R factorial. And you can reconstruct this number quickly if you spend just a little bit of time with it, okay? Just the argument again, n for the first, n minus 1 for the second, and so on. Okay, let's see a very silly example of this, right? Let's keep it there. So example, I have a race with 8 runners. So how many possibilities are there for a gold medal plus silver medal and bronze medal winners? Right? So there's a lot of possibilities, right? But how does this go? So I have a set of 8 runners and I'm selecting 3 in order, right? The order matters, right? So notice this is, if you have to reason it out, ordered selection. So when you're going to do problems from the book, at some point, this is a question you really have to focus on. Am I counting things which are ordered or not? And this is always obviously important, okay? So this is an ordered selection of 3 from 8. So I'm looking at P8, 3, right? This is the number I'm interested in. And I have a formula for it, which is 8 factorial divided by 5 factorial, which is some number. Okay, it's 336. Doesn't sound right, but that's what's on my... Okay, So is that, you see what I'm doing? That makes sense?
Yep.
All right. Okay. Here's a slightly different one. So I'm not going to illustrate this forever, right? I mean, you see one, you've seen them all. Here's a slightly different one. So how many permutations? Yeah, I didn't mention this, I should have. So if I'm talking about a permutation of a set without saying an R permutation, it means it's a permutation of all the elements in the set. Okay, I should have added this in. So how many permutations of, and I'm going to put, look, I'm going to put a little, let's add this. A permutation of a set with n elements is an n permutation. Okay. So if it doesn't say a 3 permutation, 5 permutation, just a permutation, it means you select the whole set. It's an ordered selection of the whole set. Okay. So how many permutations of the following set? So it is A, B, C, D, E, F, G, H. If that's the question, then it's silly, right? But that's not the question. So how many permutations of this contain the string, I don't like this, but ABC. So in other words, ABC are consecutive in this permutation, in this order. Okay. This is a bit trickier. We have to think about it. It's not like a direct application of what we just saw. Okay. So a nice way to think about it, and this is a very standard counting trick, is to say, okay, so I'm selecting these letters, I'm creating words, permutations of these letters, A, B, C, D, E, F, G, H, but I have a constraint, which is that A, B, and C have to be one after another in that order. So if you think of these as Scrabble ties, right? So you have all the letters A, B, C, D, E, F, G, H, but A, B, C, you're not allowed to mix them up. You have to, so think of it as a single tile that you can play with, which is A, B, C, then D, E, F, G, H, right? So if A, B, C are glued together like this, it's a single thing that you can mix around with the others, right? If you think of it this way, then obviously what you're counting are the permutations of that set, okay? So, or obviously, clearly, hopefully. Let's put this here. Okay, so we want to count the permutations of this set, right? Damn. Okay, so this is what we want to count. Okay, so ABC is just like a single block. So how many permutations are there? There are 6 elements, right? So this is P. So I'm choosing all of them, 6 out of 6. So this is P66, which is 6 factorial divided by 6 minus 6 factorial, which is 0 factorial, which is not scary because 0 factorial is 1, right? So this is 6 factorial. Okay, is this example okay? There's this added little trick in it. I feel terribly alone today. Yeah, I've got a thumbs up. Very good. Excellent. Yes. Okay. So that's the ordered part, but you have to do problems. But basically that's all there is to say about, I mean, at this moment, about ordered selections from a set. Now I would like to consider unordered selections. So let me start with a very simple example to illustrate. Okay, so here's my example. So it's the same example I had at the beginning, but rather than choosing a vice president, a president, and a treasurer, I'm just going to select a committee. Okay, so how I asked the question, how many 3-member committees can we create from a group of 5 people? Now, you see now that this is unordered because Alice, Bob, and Eve are a committee. It doesn't make any difference in which order you list them. It's the same committee. It's those 3 people, right? So notice that ordering is not relevant, right? Once I know the 3 people in the committee, I don't need to know in which order they're selected. It's just that's the committee, right? So in other words, another way to see this, what am I counting? I'm counting the number of 3-element subsets, right? So we want to count the number of 3-element subsets of a 5-element set, right? That's the thing. Rather than ordered selections, they're unordered selections. These are subsets. That's what they are. Now, surprisingly, even though from a conceptual point of view, what we're counting is easier maybe to understand, a subset is a subset, right? They are somehow a little more difficult to count, but not that much difficult. But here is the fundamental trick, okay? So let's say that I have my 5 people that I'll call 1, 2, 3, 4, 5, right? And I want to list all the committees from this set. Well, these are the 3-element subsets, so I would list them 1, 2, 3. I might not list them all because there are a few, right? 1, 2, 4, 1, 2, 5, 1, 3, 4, 1, 3, 5. Okay, let's do it. 2, 3, 4. You see, I'm writing them as sets. This is important. 2, 4, 5. I've missed one somewhere. Oh yeah, 1, 4, 5. Darn. Let's put this here. Let's be systematic. 1, 4, 5. 2, 3, 4, 2, 3, 5, 2, 4, 5, and 3, 4, 5. And I've got them all. So this is it. Okay. So these are all the 3-element subsets of this 5-element set. So there are 10. The actual number is not really interesting. The question is, how do I do this in general? How do I count these sets in general? Okay. And the trick is actually smart. You count something which appears to be more complicated, but the relationship between the two is simple, so you can count this way. So here is the observation. So observe, right? So if we counted the three permutations, we know that it's 5 factorial divided by 2 factorial. Bingo, that's it, right? So counting the 3 permutations or the ordered selections, right? It's P53, which is 5 factorial divided by 2 factorial. That's it. Okay, let's list a few of these things. So for example, I won't put I'll just list them to make it shorter, right? 1, 2, 3, 1, 3, 2, 2, 1, 3, 2, 3, 1, 3, 1, 2, 3, 2, 1. So these are the ones where I've chosen 1, 2, 3. Then there's those with 1, 2, 4, 1, 2, 4, 1, 4, 2, 2, 1, 4, 2, 4, 1, 4, 1, 2, 4, 2, 1, and so on, right? Hopefully you see what I'm trying to say, which is probably very simple, but anyway. 251, 512, 521, and so on. So I'm listing here. So I know how to count those. There's a whole bunch, right? So I know how to count those. And when I list them, I observe a connection with the unordered version is that for each one of the unordered version, I have 6 ordered versions of each, right? So that's the connection, okay? So notice for each subset, for example, 1, 2, 3, there are exactly, and how do I know that? Because basically I want to order those 3 elements. These are the 3 permutations or the permutations of 1, 2, 3, right? So there are exactly P of 3, 3, which is 3 factorial, which is 6, 3 permutations corresponding to it. Right? So for each subset, unordered, I have 6 ordered versions of that one, and it's 6 for all of them. So I get this very nice, simple connection between the unordered and ordered versions. I know how to count the ordered ones, so now I know how to count the unordered ones, right? So that's the trick. Okay, do you see what I'm talking about? Does that make sense?
Yeah, I think so.
Yeah, all right. Okay, so let's now define what we call combinations, which are the unordered versions of what we were talking about. Okay, so definition. Here I can use certainly R equals to 0 because these are subsets. But anyway, so an R combination, I personally never use that kind of terminology, but it is standard for people who do combinatorics, or very pure combinatorics. So an R combination of an n element set is an unordered selection of R elements from the set. But what is that? That's a subset of size R, right? That's all it is. Okay. This is clearer to me anyway. So C and R denotes the number of R combinations of an n element set. Right? So notice, by the way, that if R is 0, what's a subset with 0 elements? That's the empty set. How many of those are there? There's 1, and the formula will work. Okay. Okay. So the principle. Oh, is my tablet going to die? Maybe. Don't die. Sorry. No. Okay. I have no idea. So the above example illustrates the following. Okay. So what is the connection between permutations and combinations, right? If you're given an R element subset, how many permutations correspond to that set? Well, you permute the elements of that set, right? So for each subset of size R, there are there are P R, which happens to be R factorial, R permutations corresponding to it, right? So for each, you fix a subset, you can order its elements in R factorial ways to get all the R permutations corresponding to that one. And it's the same for all. So in other words, what this says is that if you count the unordered ones for each one, I'm repeating myself, but so if you count the unordered selections with R elements, each one of them, if you multiply by R factorial, there are R factorial permutations, R permutations corresponding to each one of them. So that's what I'm saying. I'm saying that P of NR is R factorial times C and R. So from this, I get that C and R is P and R divided by R factorial. So this is N factorial divided by R factorial N minus R factorial. Right? I just used the formula I had for P and R to get C and R. Okay? So you count them ordered, and you've counted them, each subset has been counted R factorial times too many times, right? Because of all the ways of permuting this subset, so you divide, okay? And it's uniform, it's the same number for each, obviously, okay? So this is the number of subsets of size R of a set with N elements, okay? That's another way of saying that. Some remarks. There's another notation for C and R, which is the following. I guess a common notation for C and R is N R like that, which is read N choose R. N choose R. In the next section, when I'm going to do the binomial theorem, I will be using this notation. It's standard. Okay, they mean the same thing. Okay, this is, and again, another way of seeing this is equal to the number of subsets of size R of a set of size N. Okay. So let's illustrate that. Let's do a very simple illustration. 4, choose 2. So what is that? That's the number of 2-element subsets of a set with 4 elements, right? So this is supposed to be 4 factorial divided by 2 factorial times 2 factorial And this is some number, which is 4 times 3 divided by 2, which is 6. Now let's check. Let's see. So I've got a set with 4 elements, and I look at the number of different 2-element sets, subsets. So there is 1, 2, there is 1, 3, there is 1, 4, there is 2, 3, there is 2, 4, and there is 3, 4. Yes, so it works. Okay, which is good news. Yeah, so that's done. That's wonderful. Here's a little application of this. Application, jeez. Illustration. Count the number of different poker hands that can be dealt from a regular 52 card deck. If you're trying to compute probabilities of certain hands at poker, this is a number that will be very useful. So what are we looking for here? So a hand in poker is 5 cards, right? So this is a 5 or standard poker. This is a 5 card selection, right? Does the order matter? Not you're dealt these cards, you can reorder them as you wish, right? So it's just those 5 cards. So this is an unordered selection, unordered, right? It makes no difference. So reorder, it's the same hand, right? So you don't want to count them differently. So what you're looking for is C52.5, or if you prefer 52, choose 5, right? So this is 52 factorial divided by 5 factorial times 47 factorial, right? So it's n factorial over n minus r factorial times r factorial. If you compute this, if you start by trying 52 factorial, that's not smart. You'd rather just simplify the 52 factorial and 47 factorial first to make the numbers. It's not a very big number, actually. It's 2,598,960. So it's not like a huge number, but still. So 2.5 million different poker hands are possible. Okay. Is that not too bad up to this point?
Yeah, that's fine.
All right. So I'm going to move on to 6.4, which is a little bit more interesting. How are we doing on time? Very good. Excellent. Excellent. Okay. 6.4. The binomial theorem. So I'm going to use these things I've just defined to do something, which is, this is really a very, very nice theorem with this has tons of applications. And this is the theorem, a theorem that when you're going to see it, you're going to say, why didn't we see this like 5 years ago? And the answer is, I don't know. It's simple. It's fairly simple, and it's really useful. You would have liked that when you were doing Cal 1. But anyway, so that's the way it is. Okay, so here is what we want to consider. So consider, we're going to do a little algebra. The product of the binomial x plus y raised to the power n. So I want to multiply x plus y by itself a large number of times, right? So this is x plus y times x plus y a whole bunch of times, like that. In fact, n times. Okay. Now, okay, so we can do that, but it turns out that there's a very simple expression for this product as a sum of products. Okay, and it's based on the distributive law. So what does the distributive law say? And I'll tell you how this works with the smaller examples, right? So the distributive law tells you how to multiply sums, okay? And it turns out that if you multiply these sums together, right, it's going to be a sum of products. But what are these products? Well, it's easy. You're going to select exactly one of those two, x or y, in each bracket, and you multiply them together. Okay, so this says, it tells you that this is a sum of products. Each product is obtained by selecting exactly one term in each bracket. Okay, so maybe you don't believe this, and that's okay. All right, so I'm going to illustrate this immediately. So x plus y. I mean, I'm going to do more than illustrate it. I'm going to almost prove it, because now you know induction. So, but I'm not going to do this formally. I don't want to go into all the details. Okay, but let's just multiply x plus y times x plus y. The distributive law says that this is x times x plus y times x plus y, right? That's what the distributive law says. And I apply it again, right? So this is xx plus xy plus yx plus yy. So you see, this is a sum of products, and look how each product is obtained. You select exactly one term in each bracket. So this one, I've selected the x in both. This one, I've selected x in the first, y in the second. This one, I've selected y in the first, x in the second. And this one, I've selected y in both, right? Okay, let's try 3. But okay, but let's do a lot of stuff at the same time. Now, this is not the way we usually write it, right? Because our product is commutative, right? So x, y, and yx, that's the same thing. So we usually write this as x squared plus 2xy plus y squared, a formula which you've seen zillions of times. Okay, not so bad. Okay, let's look at the next case. X plus y cubed. Okay, so now I've got 3 brackets. Okay, but now I can use what I've just done with 2 brackets. So this is x plus y times let's do it. I want to illustrate 2 things at the same time here. So this comes from here, right? So I'm going, I mean, basically, if you want to keep on going, you use induction to prove my claim that this is a sum of products which is obtained, blah, 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 blah. Okay, but this is what I'm doing here. So now I'm going to use the distributive law once to distribute this whole thing. And what I'm going to get is xxx plus xxy plus xyx plus xyy plus, that was the x part. And then I do the y part, yxx plus yxy plus yyx plus yyy, right? So you see that this is exactly the list of all the products you can build by selecting in each bracket either x or y, right? So you take xxx, xxy, xyx, x, and blah, 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 right? That's exactly what's going on here. Now, that's not usually the way we write it. We regroup terms which are the same because our product is commutative. So we usually rewrite this as follows. This is x cubed. Now, if you look at x squared y, you see that it appears 3 times, 3 x squared y. If you look at x y squared, it appears also 3 times, and then y cubed. Okay. Okay, and so on. All right. So every year that I teach Cal 1, I see at some point some problem which is something cubed, and I see students actually multiplying out the whole thing. And I think, why didn't they show them the binomial theorem? It's such a useful thing and easy. Okay, so let's do this. Okay, so what are these products? So what do they look like? Okay, so I've got x plus y n times multiplied like that. And I want to select in each bracket either x or y. Okay, so let's regroup them as follows. I'm going to select, let's say, r x's, and the rest will be y's. Okay, so if we select r n, yeah, okay, so yes, you can see where this might be going. So we select r x's from the brackets, and that leaves n minus r y's. So the product that we're going to get will be x to the r, y to the n minus r. This is a typical product when I'm selecting. Is everybody okay up to this point? If not, I can try to do it differently or repeat, or yeah. Okay, so I've got n brackets. I'm selecting x's and y's, and I just want to say, okay, let's select r. Let's give a name to the number of x's we choose. We choose r of them, so that leaves n minus r y's. Okay, so the products all look like that for different values of r, right? Now, so it's a sum of these things. The only question that remains, if you look at our 2 previous examples here, you see x squared appeared exactly once. There's only one way to select x in all of them, and there's only one way to select y in all of them. But xy, I can choose xy or yx, that's 2 of them. If you look at the cube, you see there's a similar pattern, but the numbers are different. So this is the question. So once I have all these selections, how many times will, let's say, if n is 6, I've got x cubed, y cubed. How many times will it pop up, right? So the question is this: how many times will x power r, y to the n minus r appear? Okay, so that's the question. But the way we phrased it, the answer is immediate. I'm selecting r x's from those brackets. I have n brackets, and I'm selecting r of those to give me x. How many ways are there to do this? It's n choose r. That's exactly it, right? So we select r brackets for the x's. From n brackets. And the order doesn't matter, right? The way I'm selecting is just, it's a subset, right? So there are n choose r ways to do this. And that's it. That's the binomial theorem. Okay, so the binomial theorem says by the distributive law, okay, so there's some induction there, but basically all these terms are a bunch of x's multiplied by a bunch of y's, for a total of n symbols. And how many times will x, r, y, n minus r appear? And choose r. So that's it. So here is the binomial theorem. Right? It says that if you compute x plus y to the n is some integer, it'll work with 0. So you choose r x's. This number can be any from 0 to n. Right? You can choose 0 x's, you can choose 1 x, you can choose 2 x's. But once you know how many you've chosen, how many times does that product x power r, y, n minus r appear? It appears and choose r. I mean, I know it looks a bit more daunting this way. I mean, it's like, you know, but all it says is something very, very combinatorial, fairly elementary, right? I wouldn't attempt to do this with 8-year-olds, you know, not this way anyway, but but it's still fairly straightforward. It's not the fundamental theorem of calculus, okay, by any means. Okay, let's take a look at this. Let's take a look at an example. Let's say that I want to compute x plus y to the power 4. So the theorem says this is the sum r equals 0 to 4 of 4, choose r, x power r, y power n minus r. So let's develop this, okay? So basically r runs from 0 to 4, and for each fixed r, I get that particular product the right number of times, okay? So this will be 4 choose 0, x power 0, y power 4, plus 4 choose 1, x power 1, y power 3, plus 4 choose 2, x2, y2. I'm not going to be able to fit everything, unfortunately. 4 choose 3, x power 3, y power 1. And finally, 4 choose 4, x power 4, y power 0. Okay, so the last thing to do if I want to expand this is to know what these coefficients are. I can use the little formula if I want. Okay, but I'm going to show you another way of doing it in just a few seconds, which will tell me that this is y power 4. I think this is correct. 4xy cubed plus 6x squared y squared plus 4x cubed y plus x power 4. Yeah, I think this is correct. Okay, so this is the binomial theorem. Oh, things are not gonna end well. Okay, so next thing is, how could we compute the n choose r's faster when n is smallish? Okay, so let me show you how we can do this. Okay, and then I'll put everything together. Okay, again, let's move back up. So the binomial theorem tells you how you can expand a nth power of a sum, right? X plus y. This is this is a polynomial, so you can use. We'll see how we can use this to our advantage by specifying what X and Y could be, for example. But the basic idea is these are products, power of X times power of Y. A certain number of times you add them up. Okay, so that's the general thing. Okay, you can use it this way. That's one way I've just expanded, but now I'd have to compute all the coefficients with the factorial function, and it's sort of, yeah, it's annoying. But there's, for small values of n, right up to 12, by hand, you can do them very, very quickly. So I'm going to show you, and this is very old. This is like thousands of years old. Okay, so this method is very old. Okay, I don't know. It's not. I don't. It's. I should have looked it up before, but it's. It was known in Asia thousands of years ago, but in Europe, this is known as Pascal's triangle. But it was known. I mean, Pascal didn't steal it. He didn't know it was known before. But here's the trick, or a trick. So this is Pascal's triangle. So here's a lemma. My tablet is going to die soon. Maybe I should just okay. Let's plug that in. Sorry, I'm gonna pause the recording. Here we go. Okay, so here's a lemma, which looks, but it's I'm going. This is the formal justification for the little trick I'm going to give you to compute these coefficients. So here is the formal lemma, which I will prove because the proof is really cute and simple and useful. So if you want to compute n plus 1 choose R, what you can do is compute, let me make 100% sure I'm not lying. You can choose R minus 1 from n, or you can choose R from n. Okay, here's I cheated and looked at my notes because I didn't want to mess up the indices, because is it R minus 1, is it n plus 1, blah blah. Actually, it should have been easy, but if you remember why this is true, the construction that I'm going to show you, you can always figure it out again. This is easy. So I have a set with n plus 1 elements. How many R element subsets? Right? So this is the left-hand side that I'm counting, right? So I want to show that it's the same as the right-hand side. So what do I do? If you look at the right-hand side, this is okay, people who do like pure combinatorics, they love this kind of proof because it's a combinatorial proof, because you're counting the same thing in two different ways and you get an identity from that. There are other ways to do this, and somehow pure combinatorialists don't. This is their like favorite kind of proof. I can understand. It's very elegant. So on the left-hand side, I'm counting the subsets of size R of a set with n plus 1 elements. Now on the other side, I should be considering n elements. So what do? Is you fix some element W in the set. Okay, so you have this set with n plus 1 elements, and you choose an element W, and you would like to count subsets of size R. There are two kinds, right? Two kinds of subsets of size R. With W, without W. Agreed? Yes, everybody agrees. Okay. And I want to count them. So if they don't contain W, what am I counting? I am counting R element subsets of the remaining N elements. So there are N choose R of these. Yes? Oh, I've lost my list of participants. Are you right? I'm choosing R elements from this big set. And now I say, okay, let's choose them without choosing W. So how many can I choose? And choose R, right? It's the number of subsets of the N elements left here. Yes?
Yeah.
Yeah, okay. So then that's N choose R. How many are there with W? Well, there's W, and then I have R minus 1 left to pick in the N remaining elements. So there are right? So you're choosing the remaining R minus 1 elements from the remaining N elements. So you see, this is exactly what this lemma says, right? So if you're choosing R elements from N plus 1, just fix an element and count those that contain it and those that don't, and you get exactly that, okay? Now, from a computer scientist or programming point of view, you can see now that if you know the coefficients for N, for the binomial theorem for power N, you can compute the next level, N plus 1, from those. You just add 2 consecutive ones, right? This is Pascal's triangle. So let's just illustrate this. Okay. So from the lemma, we get Pascal's triangle. Okay, so here is the triangle. I'm going to put some zeros here. Maybe I'll put them in red, because otherwise the thing is not going to look like a triangle. The next is this. Okay, so basically, here's the rule. We start with a row where there's a 1 and everything else is zeros. And the rule to get the next row is you add 2 consecutive values, just like the lemma told you, right? So now what you do is you add two consecutive values. Now the zeros, you don't have to put the zeros in, but it helps to bootstrap the thing, right? Okay, so what then is the next line, next row? Same thing, you add 2 consecutive. So this will be just a bunch of zeros. This will be 1, 2, 1. And I won't put the zeros from this point on, okay? Next row. So every row is obtained from the previous by adding two consecutive entries. That's the rule, okay? If you look at the lemma, what it's going to tell you is that if you start with the right values, what you're going to get are the binomial coefficients. I should have told you that that's what they're called for the next value of N. So this is 1, 3, 3, 1, 1, 4, 6, 4, 1. You might recognize, right? 1, 2, 1, x plus y squared. 1, 3, 3, 1, x plus y cubed. I'll do a few. 1, 4, 6, 4, 1. That's the one I computed. Yeah. Mm. Mm. Yeah, that's a bit far, but anyway, it's there. Sorry. Okay, so next 1, 5, 10, 10, 5, 1, 1, 6, 15. You see, I mean, this is easy. So when I say you can do this for small values, you can see you can go up to 10, 12 very, very quickly, right? So by the last lemma, for example, if I want to compute x plus y to the power 6, so notice these are the coefficients for n equals to 2. Everybody knows that. This is 3, 4, 5. These are the coefficients for power 6. So this is how I compute this thing. X power 6 plus 6. I've put the powers of x in decreasing order, but you can see that's totally symmetric, so it makes no difference. Plus 15 x power 4 y squared plus 20 x cubed y cubed plus 15 x squared, yeah, y power 4 plus 6 x y power 5 plus y power 6. Is this, yeah, I'm losing people. I'm sorry. It's too much in one day. How many of you had seen this before? Some of you might have, I mean, formally in class, I mean, not by yourselves. That doesn't count.
Yeah, I hadn't seen it in class, but I'd sort of
Yeah,
heard of it before.
yeah.
Yeah, they never showed this in.
No, you never saw this. I know. And I mean, I know I went really in depth formally with all the whole construction, but basically once you know the triangle, you can compute x plus y power, any power in is just like immediate, right? It's just like boom. And this is like super useful. So every year when I see kids in Cal 1 just like going x plus y power and just like multiplying and of course messing up, making mistakes, it's like why didn't they show them? It's just like 10 minutes. Anyway, but I'm sure you learned so many useful, interesting things instead. But let's not go there. Okay, so let's, I'm almost done. I have a feeling that okay. Sorry, I've lost my repère. My screen, it looks weird and okay. Okay, so there you go with Pascal's triangle. Let me end with a couple of applications which are really neat. Let's go here. Okay, so a couple of neat applications. So it turns out that once you have the binomial theorem and you have, and if you have calculus, I think there are some exercises in the book where you can use some baby calculus and with the binomial theorem, you can prove like really amazingly difficult formulas, identities that if you don't have that, it's just like really tough. But let me show you a few basic ones. So here's one. that I'm going to show in two different ways. So if you sum, I forgot to mention this, but these numbers n choose r, these are called the binomial coefficients for an obvious reason. In the binomial theorem, they are the coefficients of the products. So if you add all the binomial coefficients, what do you get? Let's go back over here. Let's do something. Let's just observe. So I'm going to add all the numbers in each row just to see what happens. So the first row here, I get 1. Then I get 2. 1 plus 2 plus 1 is 4. 1 plus 3 plus 3 plus 1, that's 8. 1 plus 4 plus 6 plus 4 plus 1, that is 16. You can probably guess the next. Yes, 32, 64. There seems to be something there. Now let's now take the alternating sum. So rather than add them up, you say add, subtract, add, subtract, add, subtract. Let's just see what happens. Okay, this is not, well, let's forget about that one. But this one, you'll get 0. 1 minus 2 plus 1, you get 0. 1 minus 3 plus 3 minus 1, you get 0. 1 minus 4 plus 6 minus 4 plus 1, you get 0. And you see how this is going to go, right? So if you take the alternating sum, it appears like it's always 0. If you just take the sum, it appears as though you get powers of 2. So this is true. So this is true. Here's the first proof. This is the proof that combinatorialists will like. It's a combinatorial proof. So I'm going to count to the same thing in two different ways. So what is the left-hand side? I'm adding up n choose 0, n choose 1, n choose 2, which all count the number of subsets of size 0, 1, 2, and so on. So the left-hand side is the number of subsets of an n element set. So that has to be 2 power n. So notice both sides count the number of subsets of this. Right? On the right-hand side is something we've seen several times. The power set, cardinality of the power set. On the left-hand side, this count is split up along the size of the subsets. So how many of size 0, how many of size 1, how many of size 2, right up to n. So they have to be equal. Here's the second proof, which is a proof that pure combinatorialists will not like. All right. And it uses the binomial theorem. And I like it because I'm an algebraist. So look at the binomial theorem. It says that x plus y power n is the sum r 0 to n, and choose r, x power r, y to the power n minus r. So this is a statement about polynomials. But if I replace x and y by the values that I like, it has to be true, right? This is true for, if you wish, for all x and y. What values for x and y would be a smart choice to prove what we want to prove?
Each one half?
Yes, if you take x and y equal to 1, you will get exactly what you want, right? So let x equals to y equals to 1. So you get exactly what you want. Right? Because x plus y will be 2, that's 2 power n. And on the other side, 1 power r, 1 power n minus r. That's just 1. It just disappears. Okay, so I'll let you just do that little last step. Okay. So that's the proof that the sum of each row is 2 power n. What about the alternating sum? Let's state that. If you sum r equals 0 to n minus 1 to the r and choose r, we observed experimentally for small values of n that this was 0, and it is true for all n. What's the proof? I don't know a combinatorial proof of this. Yeah, no, sorry, I do, but it's not as nice as this proof. So let's write the binomial theorem again. What values of x and y could you put in there to get what we want? Do you see? So compare this to this. No?
Is it gonna be like 1 and -1 or something?
Yeah, absolutely. Right, so let's try x equals to -1 and y equals to 1. Let's see what happens. Then I'm going to get -1 plus 1 power n equals sum r equals 0 to n, and choose r. X is -1, so that'll be -1 to the r and 1 to the power n minus r. So this is 0, and this is it. Boom. It's pretty cool. Doesn't n need to be at least 1? Yeah, you're right. You're absolutely right. Yep. If, in fact, do we need, 1? Maybe 2. You know what? I'm going to put a 2 here because I don't feel safe. So, yeah, it didn't look like it would be true for n equals to 1. Yeah, for n equals to 1 is good. It's n equals to 0, which is no good. Yes, you're right. You're right. You're right. You're good. Yes, yes, yes. Okay. Yep. Agreed. Yeah, no, 0 power 0 is undefined. There is no way to define this to, no. Yeah, 0 power 0 is just going to get you in trouble. Whatever value you try to give it, you're just going to ruin some nice identity somewhere. Yeah. It's best left undefined. Okay. I got, that's it. That's it. I don't want to do another one. So there are tons of other identities which you can prove using the binomial theorem like that, which are very cool. I know it was a lot today. So spend some time with it. But there are just like 2 or 3 fundamental ideas that I presented basically. And that was it. But there's some notation on top. And you can cure that by spending time with it. Questions?